Good evening to you all. Welcome once again to this exciting series of webinars on asset management practices, co-hosted by the South African Institute of Electrical Engineers and SAIEE Southern Africa. We've come a long way. This is our 5th series of our 7-part weekly webinars. We're almost at the end, and we truly appreciate all the support and all the people that have logged in and the questions that have come through. Today's presentation webinar is on the expansion and operations planning. My name is Refilwe Buthelezi, and I will be your host for this evening. I have my profile in front of you, so I won't read much, but I will summarize it a little bit for you, especially those people who are joining us for the first time. I'm an automation asset manager at Randwater, and my responsibility is to ensure that all the automation assets are specified, installed, operated, and maintained in order to provide levels of service at minimal lifecycle cost. I also fulfill roles in Engineering Council of South Africa and the South African Institute of Electrical Engineers. I would like to welcome you all. This is the 5th of our 7-part weekly webinar, and today's discussion is particularly on expansion and operations planning in the industry. We will then wrap up our series with a discussion on optimization of project portfolios in light of capital rationing. Be sure to join us. This evening's presentation, as mentioned earlier, is presented by Leslie Naidoo, who is a senior grid manager at Eskom. He has worked at Eskom for various years and is the senior manager for infrastructure planning in the transmission grid planning, responsible for the formulation of transmission of short, medium, and long high voltage network development and infrastructure plans. He is also a representative and is in the steering committee for Eskom research, focusing on transmission businesses. He's a member of the Department of Science and Technology, where there is research of infrastructure roadmap and at the steering committee. And in 2019, he was appointed as the transmission representative on SANRS MENCO. His qualifications are as follows. He has a B.Eng Electrical with the University of Durban-Westville, a diploma in data matrix with UNISA. He attended the graduate program in utility management with Samford Business School and has a master's in science for engineering business management with the University of Warwick and attended the senior management program SMP with Henley. The second speaker for the evening is Martin Kopa. Martin is a middle manager for system operations at Eskom. He joined Eskom in 1995 as an ENT, and in 1996 he was then appointed, and his responsibilities included calculation of protection setting for generators, MV switchgear, transmission, and distribution networks. In 2003, he joined Transmission System Operations Performance Section as a senior engineer, responsible for EHV and HV protection setting calculations, and later promoted to chief engineer position in 2006. From 2007 to date, he has been working as a middle manager in System Operations Planning Department, being responsible for providing a short-term reliability planning services and operational support to national control and other customers to enhance safe operations and quality of supply for Eskom integrated power systems. Without going any further, I do invite you to send us all the questions that you may have into the question pen, and I will ensure that I present all your questions to our presenters as they conclude their presentations this evening. I will now hand over to Engineer Naidoo to kick us off.
Good evening, distinguished guests, colleagues. My intention today is to give you a brief background into the asset investment planning for capacity expansions in the transmission network in South Africa. I will cover, basically take you through the mandate of the transmission network company. I will look at the South African Grid Code, transmission planning process model, look at some of the studies that we do in planning for the transmission system, and to conclude. Before I start, I think it's appropriate to just touch base on the transmission mandate at a fairly high level, which is basically to reliably control, maintain, plan, expand, and provide access to an interconnected transmission system, and to enable trading in energy, influence customer demand, and effect opportunities in the SADC region. Just to step back, I think most of you guys are familiar with the asset management framework as covered in the ISO55k. And today what I'm going to be focusing on is on the asset management plans, more specifically around expansion and growth planning for the system. From a transmission operating model perspective, similar to what was in the previous slide, we have the strategic imperatives and the governance processes on the top, supported by various processes in between, with the focus of making sure that we have secure and reliability supply to the end customers, which is governed by the operations and maintenance. My focus today will be on looking at the evaluation of the capability and capacity of the system to meet future requirements. And you will notice that in the decision section out here, whenever there's a request or a requirement for expansion, we always look at first and foremost, what is the existing capacity and capability of the network, and could we manage via revising operations or maintenance, or should we go towards the refurbishment side to extend or replace the existing life of the existing system? My focus will be looking at more on the expansion side, where we want to bring in additional capacity for various reasons, as I will explain going forward. Just to take a step back, the planning of the transmission system for the country is governed by the transmission license obligation. In essence, transmission is obliged to provide open and non-discriminatory access to the national transmission system. Further, the transmission system planner is required to plan and augment the transmission system in accordance with the South African Grid Code. Now, I just want to extract from the Grid Code the criteria specifically focusing on reliability, where it states that the National Transmission Company shall develop the transmission system on the basis of justifiable redundancy. What that means is that would a single circuit out of action, be it a transformer or a reactive compensation device that fails, it shall be possible to supply the entire load under all credible system operating conditions. Further, it states that the investment in the transmission system to satisfy the minimum redundancy requirements, which we often refer to as N-1, shall be on a deterministic basis with no financial justification required. The important thing to remember here, it has to be on a deterministic basis, which means that if you know that there's going to be a problem on the system, do not wait for the problem to happen. You must resolve it or have plans in place to address the problems before they occur. Now, if you look at the reliability criteria from, as expected from the regulator of the country, that's NERSA, the National Energy Regulator, it calls for a reliable transmission system made up of the transmission operator as well as the grids. Now, what NERSA does is, through the license, it allows transmission to earn a return on its assets. And how this goes about is that the grid code defines the reliability criteria and the justification criteria for transmission to make investments onto its system. However, these investments have to meet the prudency test of least economic cost investments in the network. And by so doing, via the multi-year price determination methodology, transmission is allowed to earn a return on its assets that is equitable to its investments. Further, NERSA does an annual audit on the transmission investments to make sure that they conform to the criteria that's defined in the grid code and making sure that the country gets the least economic cost investments in the network. Now, when we look at the investment criteria as well as that's also defined in section 7.7 of the South African Grid Code, it stipulates typically 4 criteria that we justify projects in transmission. Typically, the first one that deals with the least economic cost, where projects are justified that brings about improvements in quality of supply to the customers. And in this case, what we are trying to find out is the weighted average customer interruption cost versus the break-even cost of supplying that energy. I'll go into more details in the next slide. Typical projects or investment plans that are justified on this criteria covers customer connections and reliability projects to meet the minimum N-1 criteria. Then there's the second criteria, which looks at cost reduction investments. Now, these are investments that optimize or reduce the operations and maintenance costs or reduce network losses on the system. And typically, you would do a net present value calculation to analyze and determine if the project is viable. Here again, you could use this criteria to justify reliability projects based on savings in losses, as well as looking at refurbishment projects. Then comes the other criteria that leans towards statutory investments. Here you use this criteria to justify investments that are legally required, irrespective of whether any economic benefit is likely to accrue. And typically, you will use this criteria when you're adjusting projects to meet legislative requirements. Safety aspect examples are the safety aspects or the national nuclear requirements. And projects that fall in this category of investments relate more to safety related projects, reliability projects as well, and environmental impact assessments. The fourth criteria deals with strategic investments. And these are investments where you are looking at typically for your servitudes, strategic spares, where it is difficult to justify projects based on the above 3 criteria, then you will go down to the strategic investments. Some of the examples here will be like your secondary plant equipment, your control systems, protection equipment that you can justify on the strategic basis. Moving on from the criteria, I just want to touch base on the least economic cost criteria, because this is the one that is more applicable to asset investments for capacity expansions. what you're trying to do is, first and foremost, is to understand the economic cost of not providing that supply. And what we do here is we look at the cost of unserved energy, which is basically the weighted average cost of the customer interruption. And what we get out here at each point of connection or supply, we look at the customer mix, whether it's agricultural, mining, industrial, and then we come up with a prorated average cost. So what it tells us is, if we do not provide the supply, this is the cost to the economy of the country. On the other side, we look at what would it cost us to invest, and we calculate the break-even cost of the unserved energy. And that is typically gathered by taking the equal annual capital cost, basically finding out what is the annual repayments, and we divide that by the energy, the effective energy that's, or the expected energy that would not be supplied, to get the what you call the rands per kilowatt hour. Then we do a comparison, and if the break-even cost of the unserved energy is less than the weighted average cost of the customer interruption, then the project is deemed to be viable to go into execution. What it means, in essence, is that the investment is going to be to the benefit of the economy of the country. Now, going forward, from a planning perspective, the first phase is governed by policy and regulation that is driven mainly from the Department of Energy, whereby the Integrated Resource Plan is the governing document that stipulates the energy requirements from a demand perspective as well as from a generation perspective for the country into the future. From a planning perspective, what we need to do is to translate the information from the Integrated Resource Plan in terms of disaggregating the generation pattern for the country spatially across the regions, knowing well that the IRP has the generation pattern for the country at a national level. Likewise, the expected demand is also provided at national level. So our role as planners is to take this and translate it spatially across the country. And to do that, we develop a strategic strategic plan that looks at the various scenarios, and we come up with also looking at plans from our distribution areas across the country, the master plans, and then taking all these plans together with the operations appraisal, which looks at the current concerns or constraints on the network, with applications that we have processed in collaboration with the refurbishment plans, and ultimately we come up with a 10-year transmission development plan, which ultimately leads to the investment plan for the country. Just to give you a very simplistic or high-level view of the investment planning model, as I mentioned, on the demand and generation side coming from the IRP, what we do with that information based on the existing network, looking at its capability and capacity with the necessary standards, regulations, the adequacy criteria, we ultimately come up with the network expansion plans for the country. Now this on the top block is addressing the new capacity that will be required in the system or on the system to meet the future requirements, be it for generation or for demand. Also, in the same token, we have the existing asset base, and this is based on the life cycle asset management plans, ultimately to derive the asset refurbishment plans. So you have the network expansion plans looking into the future, and on the other side, you have the asset refurbishment plans, which considers the existing infrastructure. Now, what we need to do is to align these things to make sure that we have the most optimized plan. We use prioritization criteria, which I'll explain a little later on. And more importantly, having the plans, we need to know the executability as well as the fundings that are required, or the Capex that's required to make sure that these plans can go into execution. And ultimately, we have a prioritized list of the transmission development plan for the next 10 years. Now, from the grid code, when we're going into the planning process, all approved capital projects are subject to the grid code compliance audit by NERSA, as I mentioned before. In essence, from the grid code, it starts off with identifying the need, what's the reason for the future plans, defining the problems, coming up with the generation of generating alternative solutions, doing a techno-economic evaluation on the various alternatives, selecting the preferred option for the solution, as well as compiling the business case, and then getting the projects justified and approved. Now, from the processes, we move to what drives the drivers or the reasons behind transmission's capacity expansion. Now, the main drivers in this area relate to network strengthening to address existing customer expansion requirements, also to connect new customers based on the anticipated demand growth, the connection of new generation plants, that's both the Eskom fleet as well as the independent power producers, looking at the grid code reliability investments, considering a mitigation of fault level exceedances based on both on the existing system as well as on the anticipated future network requirements, because as the network evolves, so does the impedance changes on the network, and that could increase the fault levels. Another key factor to consider is the resolution of quality of supply excursions to the customer base, and securing servitudes and environmental authorizations for future power corridors for new transmission investments. And lastly, to look at compliance from a regulatory, safety, environmental aspects as well. Now, going on from the drivers, once you've got all this information together, based using simulation tools, power system simulation tools, these are the typical planning studies that the planners would consider in determining the future infrastructure requirements. I will not go into too much of detail on this. My colleague in the next presentation will share much more details on the various levels of studies that are done. But just to emphasize, we normally start off with the first, the steady state load flow studies to identify the shortcomings on the existing network from its capability and capacity perspective. Then we would look at the transmission losses, and this is extracted from the load flows and is used to assist in the selection of the best techno-economic solution to compile business cases for the chosen options. As well as I mentioned, the fault level analysis, and this is these are tests or studies performed to ensure that whatever infrastructure that you're putting onto the ground does not impact or exceed the equipment ratings and cause undue problems on the network. Then we move on to voltage stability assessments, and these are conducted for network areas that have voltage constraints or for reactive power allocation optimizations via model analysis. The other important study that we do is looking at transients from a small signal perspective, mainly when you're connecting generators or large-scale generators onto the power system, to make sure that the system remains synchronism as a result of small signal disturbances. When we're bringing on capacitors onto the system, mainly shunt capacitors, we have to do the harmonic resonance studies to determine if there's going to be any harmonic filter requirements to compensate for any harmonics that are generated. And then we move on to more specialized studies. This is when you have series compensated networks, especially in areas close to where generators are, that we need to do a frequency scan on the system to make sure that there's no series compensation, or if there are series compensation requirements. Moving on from the planning studies, I just want to give you a brief overview of what the transmission 10-year development plan consists of. Now, the information and the details around this is provided on the Eskom internet, and if you have a chance, you can go into onto the site and do a search on the Transmission Development Plan and you'll find the details. So over the next 10 years, as you can see from the picture presented, a substantial amount of infrastructure investments are required across the country to meet the anticipated growth demand, as well as the generation connections. Just as an example, on the northern parts of the country, you will notice that there's the Medupi integration coming in, and then we've also got the Kusile integration. That's the Eskom fleet of generators that needs to be integrated. Whereas all over the other countries, other parts of the country, we are doing a fair amount of strengthening, mainly to resolve existing network constraints, to make sure that the capacity is adequate and reliable from a security of supply perspective, as well as in the Northern Cape, Northwest Province, the Western Cape and the Eastern Cape, mainly investments associated with the anticipated renewable energy that's been proposed in the Integrated Resource Plan, the latest one being the IRP 2019. The next slide just gives you an indication in terms of the amount of lines and transformations that will be implemented or will be required per province across the country. So within the next 10 years, we're looking at roughly just over 7,000 kilometers of lines that needs to be built, as well as about 43 gigavars of transformation capacity that will be required. So this is a fair amount of investment in the new assets that will be required across the network to make sure that the network is adequate and capable to meet the various needs as identified by the planners during the studies to come up with this development plan. Now, looking at the plan out here and the substantial amount of investments that are required, the next slide will give you an indication of the capital requirements. So over the 10-year period, you will notice, and my focus is more on the capacity expansion plans, we're looking at about 78 billion rand that will be required to meet the aspirations of the transmission development plan. And yeah, I must be cautious to say that this is the plan. It is what is required by the network based on the set of assumptions that was used in the planning phase. And the assumptions predominantly to cover the needs of reliability, new generation requirements, as well as demand on the system, and more importantly, issues of resolving fault level implications. So a fair amount of capital will be required. However, it's not necessarily that all these projects will be successful, because we are, unfortunately, as much as you want to have all these plans implemented, but you have competing objectives, and there's also capital constraints that have to be considered. So in order to address those issues, we need to look at how do we optimize the capital plan so that the best projects, or the most projects that are going to give you the best value for money, gets approved and gets into execution. So in order to do that, to optimize the plan, we follow a process of prioritization where it's a two-stage process. The first stage is looking at a quantitative analysis, and in the quantitative analysis, we look at the impacts to the economy of the country in terms of the load at risk, what's the probability of failure, what additional capacity will be required, and more importantly, what's the bang for buck for the amount of money that you will invest in these asset investments. What value are you going to get out of it? And in the second stage, we look at more qualitative analysis. And in the qualitative analysis perspective, we address the factors relating to the project readiness. Are the servitudes available? Are we not going to end up in cases of expropriation? Because with all the money in the world, if you do not have the servitudes and if the project is not ready, it would not be able to go into execution. So rather take the capital and make it available to another project of equal or importance that is ready to go into execution. So once we've done the first and second stage of the prioritization, we end up with a sort of a list of the overall score for each and every project that we can rank in the portfolio, and thereby decide on allocating of Capex for these projects to go into execution. So in conclusion, I would like to emphasize that the main purpose of the transmission's capacity expansion plans are to, first and foremost, resolve known and anticipated system reliability constraints from a security of supply perspective, ensure that the plans in place to address the demand growth for the country, ensure plans are in place to accommodate the anticipated generation capacity requirements, and to enable the strategic acquisition of servitudes for future transmission power corridors, as well as to provide input into the organization's capital infrastructure investment plans. So with that, I'd like to hand over to my colleague, Martin Kopa from our system operations area, who will take us more towards the operations planning in a real-time environment. Martin, over to you.
Thanks, Leslie. I will take you through the operations planning functions in the utility. What we'll actually be looking at, we'll be looking at the mandate and the role of the system operator. We look at the risk-based IPS operations of appraisal. We look at the appraisal of the system expansion plans, the one that Leslie was talking about. We look at the specialized system capacity studies. And we'll also look at the system integrity protection schemes. And then we'll finish with the wide area monitoring systems. In the role of the system operator, if you look at the role of the system operator, you can see that you've got generation that makes electricity, you've got transmission and distribution that transport electricity, customer services sells electricity. Now, system operator now plays a role of ensuring continuous delivery of quality electricity by maintaining stable network. And then for that now, we can actually call it a supervisor of electricity transport and distribution. If we look at the mandate of the system operator is to control the operations of and be responsible for the short-term reliability of the interconnected power system as defined in the grid code. And with that, if you look at the operations planning role within the system operator now, is to provide the short-term reliability planning service and operational support to national control and to enhance safe operations and security of supply of Eskom IPS. Here we're looking at the entire Eskom IPS, which shifts 240 terawatt-hour of energy a year, earning the party's revenue of about 214 billion. Now, I want to bring the context now of system operability. When we talk about system operability in this context, we actually are saying we're defining a stable and reliable power system that has ability to maintain and to remain intact, and can sustain with no loss of load for more probable contingency occurring. We've seen, if you look at the asset management plans, you will see that operational or flexibility planning will form part of the asset management. That will be now for asset capacity. When you look at the activities now of the system operator, you will see that from a year ahead to about 2 weeks, you have operations planning. But in this case, we're not only talking about operation planning or system analysis studies. We're also talking about other plans like generation outage scheduling. You're also looking at load forecasting. But in this particular case, we're only concentrating on the operations planning. And that in the 2 weeks time now, that's where the scheduling is happening. And then the real-time operation, it happens on the day. And because remember, we are running a real-time operations. This is when we look at it now. But after the fact, that's where we're looking at what happened, and we do the investigation and see where we can improve. If we look at the system operations process, what normally happens is that the studies are initiated when we have identified a problem. It could be coming from anywhere in Eskom. They'll say, okay, we have this problem. But now when we get into the process itself now, we'll have to start by modeling the system where we actually define the problem and we collect data and we understand what the problem is about. Then from there, we do the simulation because we use a lot of simulation tools to do that, and we do the analysis. Then after we've analyzed the problem, and then we move on to solving the problem, that's where we actually formulate the solution. And the end result of that will be to document the solution in a report and use that to give it to the customer, and the customer will give feedback. And the resources that will be used for that will actually be, your simulation tools, your policies, your guidelines, your standards, and the database and other reports. And the controls for that will depend on, the allocated time for the project and also the agency of the project. Now, one of the main functions that we do in operations planning is we do the operations appraisal. And the operations appraisal is actually a critical analysis of the whole IPS to determine potential operational weaknesses in the system when stretched to a credible operational limit, as would be in during the peak time. That's when it's winter now, you know that you'll have the peak time there, and then we assess that to see when it is stretched to that, how it will fare. Now, the results of that will be shared obviously with the business and the senior leadership, and it's actually a comprehensive view of the current and the future operational risks that we would have to determine. And that document serves as an input into Leslie's a process where we actually identify future strengthening needs for the IPS. And then the kind of studies that are done there, we look at, we assess the system against, we look at the thermal limits, we look at the voltage limits, reactive power limits, voltage stability limits as specified in the operational security guideline. And the system operational security guideline is actually based also on the grid code. This is just a typical, a time of system peak, where, as you know, the load profile we have a peak in the morning, and then we have a peak in the evening. Now, this is the peak that we actually assess, the network on. We stretch it to this level, and if you look at this profile, you can actually see here we have the dispatchable and non-dispatchable generation. It means, the fleet that we have, and also the RPPs, which are non-dispatchable, and then this will only be the dispatchable thing. But now, when you look at that peak, that's when you actually do your ops appraisal. And now the studies that you do, the contingency studies that you perform at time of system peak, you look at system health studies. This one, you assess risk for violation with the system intact. The system as is, you check if you have any violations, and then you do the N-1 in order to assess, the impact of the equipment tripping under peak conditions. When everything is okay, then you have a contingency. You assess that. You assess your system in that condition. You also look at the N-2 for all combination of double contingencies in order to assess the impact of equipment tripping during peak condition while the equipment is out of service. This could be, your planned outage or your forced outage due to maybe due to maintenance as well. And then the other part that we look at the transformer loading. And in this case, we check if, if you have, say, maybe for instance, your unfirm transformation. The unfirm transformation in this case we define as if you have two transformers and one trips, now the remaining transformer should be able to carry the entire load. Now, if you cannot do that, then we list that as unfirm. And we also look at transformer loaded between 80 to 100%. And then this trend now is done over a period of a year. And we also look at the load sharing factor, which is now the underlying network that supports those substations that you are assessing. And then also we appraise the system expansion plans, the ones that Leslie have actually talked about. What we do now, we look at future network expansion and strengthening plans, and we identify them, because obviously we would have identified with the ops appraisal. Now we have to appraise those. Although we know that the best techno-economic decision was actually used to come up with these plans, we still need to make sure that these plans are evaluated against operational criteria to assess their operability. And also, as part of the development and integration project requirement, we also look at, we have to conduct this to make sure that when a final solution has been given, it would have been tested for operability. Should we get any problems, or should we identify operational problems in this case, what we do, we normally come up with mitigation strategies. An example could be, say, maybe if we were appraising a power station and we find out that it does not meet the grid code compliant, what we will do, we will come up with a scheme to make sure that we still, comply with the grid code. The other studies that we do contingency analysis and mitigation plans. In this case, the daily requests from equipment outage for maintenance are received and assessed for posing risk of causing violations of system security. When an outage is taken, we have to assess that and see that it will not now create a problem. And then in an event where there is a problem, then we come up with recommendation. We could move the outage maybe to a time slot where there is no a high load, and like in other cases over the weekends or maybe at night, to say maybe this is the period that you must actually take your outage. And then now if you look at now the process that we follow, when we get that outage request from the system, what we normally do, we assess if it and we check for compliance. If it doesn't comply, we turn down the outage. But if it complies, then we request studies, but we only request studies for more complicated outages. The easier outages, like if we know that no, this one is an easy outage, we can confirm an outage. But if not, we will request a study, and the study will be done and make sure that we don't actually violate the system security. And the other studies that we do, we actually help with the emergency preparedness studies. And here we look at now the restoration plans for the transmission substation following the loss of equipment and subsequent loss of supply from a station. And this also, when we also do studies to assist with the system restoration of the entire IPS after a blackout. We have to make sure that, should we have a blackout, we must know how to start the system from the blackout condition. And these are the studies that we also provide as ops planning. Now we come into the transient stability studies. Leslie has touched on this. Now, to define what a transient stability is, if you look at the definition from Kundu in the Power System Stability and Control book, he says the transient stability is the ability of the power system to maintain synchronism when subjected to a severe transient disturbance, such as a fault on transmission equipment or loss of generation of or loss of a large load. And now in this case now, what we know that if we're talking transient stability, it means that falls under the classification of the angular stability, where we look at the ability to maintain synchronism. If a machine there is transiently stable, it means now it can maintain the synchronism with the entire system. Basically, the torque balance of synchronous machine is we have that. And now that happens when we actually get a large disturbance in a system. When we have a fault in the system, that's when you get a transient a stability case. But for the small signal stability case, which I will talk about later, it's when now you actually have insufficient damping. And in this case, we're looking at the changes, the small changes of generation and loads that might end up with insufficient, with small signal instability. Now I've actually put here to explain what transient stability is. If you look at now the relationship between the power that you generate and the load angle inside the generator, this is where you'll find that if you plot that relationship, you will have this equal area criteria curve, where you say ideally you should actually be operating at an equilibrium where the angle is roughly about 35 degrees, and the power will be obviously based on the mechanical power. It could be your turbine, it could be your other source of generation. Now, if you're operating at this point and you have a fault, now your angle will open up, and then depending on when you actually clear the fault, you have to actually oscillate back to another equilibrium. But now if you're transiently unstable, you will not, your oscillations will actually grow. It will not go back to the other equilibrium position. Now, if we look at small signal stability, we define this as a system that occurs typically due to small variation in generation and load. If you trip a generator here, or you trip a load there, and your network is weak, you will have all these oscillations. And now I can actually show you the analogy of the mechanical spring, where you've got two masses and a spring inside. Now, if you excite this, and it means now if you've got the inertia on both sides and you've got the weak interconnection, then you will have oscillations. Now the system is like that as well. If you look at our system here, you might see that we might take this as our own system, and we might take this as the system in the neighboring countries, because we are interconnected. But the connection that we have there is weak. What normally happens is that what we ideally, these modes of oscillation will happen as we trip generators or we trip loads. But ideally, these must be the local modes. They must die. If we have enough damping, all modes will have the positive damp, and then they will die down. The oscillations will die. But now, if we don't have that, then it means the oscillations will grow. And if oscillations grow, that might break the power system. And this is what happens when we get blackouts in the system. But in this case, now we study the small signal to establish if sufficient damping of the oscillation exists, and also to make sure that we correct the tuning of the power system stabilizers. These are the AVRs in the machine to make sure that when we get the oscillations, we are able to damp them. Now, there is the wide area monitoring system. This is the system that we've actually put on the network to make sure that, you know, we have a better situational awareness, observability of the system. Now, WEMS is actually the interconnected system of controllers and communication networks. We use here the phaser measurement unit technology to do that. What we have here, we have the IP-based connection, and then what we also do now, we monitor now at different points in the network. What the observation of that we make there is, for instance, for voltage, magnitude, the angles, the frequencies, and the oscillations that I was talking about, we actually monitor them using these PMUs, and we make sure that, you know, we have now a better view of the power system, because in a steady state kind of a situation, you might think that you're okay, but the dynamics that you have to make sure that you pick up is you can only pick up with the wide area monitoring system, because your SCADA system it doesn't have high sampling rate, and it cannot pick this up, because this one is actually in microseconds that you are able to pick up and observe the situational awareness of the IPS. Then with everything we look at, obviously, if the system has to go and if we have to have faults on the system, we should be able to have a system that is flexible to make sure that, you know, we are able to correct it. This is when now we bring the system integrity protection schemes. These ones are, you know, they include the design and to ensure the integrity of the and stability of the power system, and can include the following. We can look at under frequency load shedding, where we have relays that are armed to make sure that if there is an imbalance between the generation and the consumption, then we trip, you know, the load to make sure that we bring the balance back. And also we look at the, you know, the under voltage, the out of step generator drop-in scheme, where if your machines in the south are now reacting with the machines in the north, you can create islands. And then also, what is also important, this is what I've mentioned as well, the transient stability scheme, to make sure that if you know that your station does not comply with the grid code in terms of the transient stability, you have to put a scheme to make sure that you drop generators when you are faced with faults. And also the intertripping schemes, when you know that, you know, if you lose this load, then you have to trip a generator, or you have to do something. Those are the schemes that we actually have and we put on the system. And these will come from the studies that we actually conduct with simulation tools. And after then, we put all these solutions. In conclusion, if you look at the system operability as studies, now they form a key in ensuring that the IPS is actually stable and reliable. And also operational flexibility of the IPS is achieved through the special protection scheme, as I mentioned. And then the use of WEMS has improved the situational awareness of the IPS, and also the operations appraisal report that we produce. It also assists, you know, with the whole issue of strategic space location. We know that if you know where your risks are, you can locate the strategic space in a way that when something happens, then you can be able to respond and minimize the outage period. And also there is also the introduction on inverter-based renewable generation that has brought new operational challenges in the system. And this now, we're actually talking things like, you know, our inertia has now gone down and everything, but with the studies that we do, we try to make sure that we are able to respond now to all these challenges that we are faced with. Thank you. In that case, I will hand it over to Refilwe, the moderator.
Thank you so much, Martin and Leslie. I'm going to now open the floor for questions. But before I do that, I'd like to apologize for the minor glitch that we had earlier. I have 99 problems, but a mute button has never been one of them until today. But it's the technology we deal with. Okay, without wasting any more time, I'll go to the questions. I have a question here from Duduzi. What is the view of the fourth industrial technology on reliability solutions in power stations? And what is the LCM strategy that Eskom is using to sustain reliable power stations? I think this is for Leslie.
Okay, the first question, Refilwe, thank you, is to do with the fourth industrial revolution in power stations. But I think he's probably looking at more the power system. And I think it's the same that applies. Yes, looking at latest technologies that are available and applicable for our solutions, I must state that we have a fully sort of automated system from the National Controls Center that controls, operates, and maintains the entire interconnected power system across the country, and as well as with our interconnected neighbors. And to a large extent, that is relying on state-of-the-art technology. May not be with the cutting-edge latest technologies, but yes, over the years, we have been using state-of-the-art technologies. Going forward, I can only see improvements in reliability with the newer technologies as they become mature and ready for applications into our systems going forward. The second question, Refilwe, I think it was also similar. What was it was talking about?
Yes, it was similar. I think you've somehow answered it. Unless if you want to add anything else, it was regarding the LCM.
Okay, I must also emphasize that to incorporate the newer technologies of the future on all our major power lines across the country, we have rolled out fiber. So we have ample bandwidth and the technology in readiness to incorporate whatever the new technologies that are coming up into the future. We also have implemented substation, or we are looking into the future. We have already commissioned a fully automated substation based on the IEC 61850 protocol down at Stickland in the Western Cape region. So we are geared towards embracing technologies of the future.
Okay, thank you very much, Leslie. I have another question here from Kanyiso. He's actually sent 4. I will choose one, Kanyiso. What are the resolutions for load shedding capacity planning since the country is experiencing such problems, which is affecting the productivity or services and economy of its customers?
I think Martin can handle it.
Yes, this is directed to you, Martin.
Yeah, I think what we are currently doing, because now we have to understand why are we load shedding. The reason that we load shedding is not actually coming from the network side of things. It's the whole issue of not having enough generation in the system. But now that we know that it was because of the maintenance of the power stations and so on. But they are addressing that. Now currently what is happening is that because we have identified what the problem is and we are solving that problem, now as soon as we are done with this maintenance regime, we don't expect load shedding to be happening as often as obviously there will be cases where a plant fails, but with good maintenance, that is the strategy that we actually taking to make sure that we limit the load shedding.
Okay. Then what are your views on the effects of renewable energy plants on the stability of the Eskom grid?
Okay, I can pick that up there.
Okay.
At this point in time, I think we've got close to just over 5 gigs of renewables, combinations of solar PV and wind connected onto our system. In terms of the reliability, if I can just get that, you was talking about the reliability of the system. Currently, right up to the bid window 4, we haven't seen or we haven't expected any major problems on the network. We've managed to accommodate it quite adequately. However, having said that, there are times, especially early hours of the morning, when you have substantial amount of wind that's onto the system, but the demand is not there for it. So there is the possibility of, in certain cases or instances, that we'll have to curtail that generation. Going forward, there's a huge appetite for renewable energies coming onto the system, at least in the next 5 to 10 years. Now, as Martin mentioned early on, we need to do further analysis to more so from a network stability perspective, as well as to analyze the inertia impacts if they're going to occur. The beauty part is we have solutions that can resolve these problems. So that's why the emphasis on the future planning is so important, that if we have the adequate information upfront, we can analyze the power system, analyze its behavior, and then justify appropriate solutions to resolve any anticipated problems that we would foresee.
And maybe to add also, if you look at from the upside, you know, we're looking at we're doing research on how to, you know, to make sure that we monitor the inertia of the system, because that talks to, you know, the whole issue of the impact of reliability of renewable energy into the reliability of the power system. And then with that, if we make sure that, you know, we are able to monitor that in real time, we can take appropriate action before, you know, we have, you know, negative impact onto the reliability of the network.
Yeah. I've got a lot more questions to ask. They're coming in thick and fast, but can I just ask one more? And I think what we'll do, colleagues, is we will then post our questions and answers to the relevant people. And those that have missed the webinar can catch it on our YouTube channel. The subscription is there below. The last question I'm asking is, how does illegal connection of the network affect capacity planning? And what are the plans that you have to ensure that you resolve this issue?
With great difficulty.
Yeah.
I think we've experienced it in Gauteng the other day, or as late as yesterday, if I recall, watching the news. The challenge is we do not have control of the illegal connections. The only time you realize that you've got a problem is like when the transformer packed up here in the south of Johannesburg, and as a direct result of illegal connections, which impacts the network from an overloading perspective. And because of the socio-economic problems, it makes it even difficult for us to go and do a proper analysis out there. So once you sort those problems out, it becomes extremely difficult. Now, fortunately, when we plan the power system, Martin mentioned some of the protection systems that we have in place. I can say, fortunately, at a transmission level, we do not have experienced so much of those problems. Our big problem on the transmission system is vandalism and theft of what you call us now structures. But where the problem is mostly on the municipality networks and in our distribution networks, where we have a lot of illegal connections at the end of line supplying. And yes, it's a major concern. We are aware of it, and we have to take appropriate steps to try and prevent large-scale problems.
Yeah, No, definitely. And in some countries, they recommend measuring and reporting the system inertia on an annual basis to track stability of IPSs. Does Eskom do this, or would you recommend it?
What we said we are researching that. There is a work group that is currently looking at how we go about doing it. We've looked at the Irish grid and the UK grid to make sure that, because I know that they are doing it, but to say how are we going to do it on our side to make sure that it talks to what we do this side.
Okay. No, thank you very much.
If I can come in there just to have the future network, if you go 10 years into the future, with the decommissioning plan of some of our thermal stations, because the inertia on the current system it's a natural phenomenon from our synchronous generators that provides the adequate adequate inertia for the system. But into the future, as you decommission some of the larger power stations, the thermal power plants, and you compensate that with large-scale renewables, then you're going to see the impacts of inertia, and that's when what Martin was talking about, we'll have to have additional precautionary measures or systems put in place to compensate for the inertia and frequency control of the system.
No, that makes sense. Thank you so much, gentlemen. What we will do is we will send all the questions to you, and hopefully you'll then respond in writing, and we will send it through to all our listeners today. Without further ado, I'd like to thank all the listeners for coming in today and spending some time with us, and also invite you all to next week's webinar, which is looking at asset condition assessment. Our presenters will be Prince Moyo. I'm sure now you are all familiar with Prince, if you've been following our series, and Graham Fogel, who also presented 2 of our webinars earlier in the series. From my side, I really appreciate you joining and invite you to come and join us next week. Thank you so much, and goodbye.
Thank you, Refilwe. Thank you, Martin.
Thanks, Leslie.
Okay.